Hello, everybody. So we should have left off with this slide last time where we ended our discussion with the question, is acceleration a vector or a scalar quantity? Now, if we answered that question, we should know that if we answer that question properly, we should know that acceleration is a vector quantity. So that should answer that question. Now, let's move forward from there. And let's talk about order of magnitude and SI units. So SI units, or the System International units, are the units we use in science. These are the units that we are going to use during all of our scientific investigations. As you are well aware of, or at least you should be by this point in your lifetime, there are two major units used in the world. There is the English units. Those are the ones you are accustomed to. Those are pounds. Those are feet. Those are miles. These are all English units. However, in science, we prefer the SI units. The SI units, also known as the metric system. SI units is the standard system agreed upon by scientists and mathematicians. It is agreed upon by scientists and mathematicians. When we make calculations in science, we use that SI system. We will always use SI units. The fundamental units of the SI system are as follows. So for length, we have the meter. For mass, we have So for length in the SI units, we have the meter. In mass, we have the kilogram. In time, we have seconds. You should be familiar with these three. And as we learn about electrical force and electrical charge, the coulomb is our standard fundamental unit in the SI system for electric charge. So, go ahead and on your the right side of your notebook, as it instructs you to, write this table out and compare. It should say right. It says left, but it should say right. Let's cross that out. Put right. And compare the SI units that the English system uses as compared to the SI units in length, mass, time, and electric charge. So go ahead and take some time now for that. All right, so order of magnitude as it relates to SI units. The metric system is convenient for scientific and engineering and math calculations because units are categorized by factors of 10. It's a very, as you get used to it, it's a very elegant system. It makes conversions very easy. Order of magnitude refers to the scale of a value expressed in the metric system. Each power of 10 in the metric system represents a different order of magnitude. So, for example, we have 10 to the first power, 10 to the second power, and 10 to the third power. All three of these are different orders of magnitude. Any quantities that can be expressed as a product of a specific power are said to be in the same order of magnitude. So 800 can be written as 8 times 10 to the 2 in what we call scientific notation. This is scientific notation here. And 450 can be written as 4.5 excuse me, 4.5 times 10 to the 2 as well. Notice the 10 to the 2. 10 to the 2. That is the order of magnitude in scientific notation. This indicates to us that 800 and 450 are in the same order of magnitude. Now this is very intuitive because we can understand what 800 and 450 are much easier. But as we get into larger and larger numbers, when we get to something like 4.78 times 10 to the 27 or 5.3 times 10 to the 27, they're also, both of these numbers that I just made up here, these are both in the same order of magnitude too as well. But if we were to write these out, I'm just going to have to move up here for some real estate, but if I was to write these out, I would be writing out 4, 7, 8, and then it would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0. I'm going to run out of space here. It's going to be, in fact, 5 more zeros. So you can see very quickly, I'll try to put in commas at each 3-digit. I'm not even sure. This would be, that would be a million, this would be a billion, this would be a trillion. So that's a large number, basically. That's a large number. This is where order of magnitude can help us better comprehend what we are measuring. 4.78 times 10 to the 27. It lets us know, just looking at that exponent, we've got a really big number here without having to try to fit this number on one page. Order of magnitude is our friend. Though it might seem a little bit weird right now, it is our friend. So here we have a nice table that you can record in your notebook if you would like. It's a good sort of reference point for order of magnitude. It also happens to give us the many prefixes that we use when we are at different orders of magnitude in the metric system. So we have exa, that is 10 to the 18th power. That's exameter. Exameter is the distance, so 1 exameter would be the distance light travels in a century. That is how far light would travel in 100 years. And light travels very, very fast. So this is a very large distance. This is a very large distance. A petosecond, 10 to the 15th. It is 10 to the 15 seconds. And that a petosecond, a single petosecond, is 30 million years. 30 million years. The lifespan of the human species is only about... Humans have only existed on... The human species has only existed on this planet about 150 million years. So if we went a petosecond back in time, the human species wouldn't exist. A terawatt, that is 10 to the 12. Tera is our prefix for units of 10 to the 12 order of magnitude. That is a very powerful laser output. Gigahertz. So we often hear about gigahertz expressed as our the size of or the speed of computers. So that is 10 to the 9 order of magnitude, and a gigahertz is a frequency, very high microwave frequency. A megacurie, that is 10 to the 6, that is very high radioactivity. A kilometer, now we're getting to some things we might be more familiar with the kilometer. That's 10 to the 3 order of magnitude. That is about a 6/10 of a mile. 6/10 of a mile being the English unit. A hectoliter. A hecto is what we use for 10 to the 2 order of magnitude. A hectoliter is 26 gallons, so that's still a very large volume. And then 10 to the 1 is a decagram. The decagram is about a teaspoon of butter. When we get down here to the 0 order of magnitude, that's where our grams, meters, liters, this is the order of magnitude where those exist. They don't have a prefix. There is no prefix. So they're just grams, meters, and liters, or seconds, watts, curies, hertz. All of those fall into the 0 order of magnitude. Now, if we go down the chart, so up here is our grams, liters, and meters. And now we're going down order of magnitude. So a deciliter is 10 to the negative 1. That's less than half of a soda. So your typical soda is that's less than half. A centimeter. So we've probably measured in centimeters. Our prefix centa and c is 10 to the negative 2. That is about the thickness of your fingertips. A millimeter, another measuring unit you should be familiar with. That's 10 to the negative 3, and that is about the size of a flea at its shoulders. A micrometer, that is 10 to the negative 6. Now we're getting even smaller. This is the detail we see under a microscope, is a micrometer. A nanogram, that is 10 to the negative 9, still getting smaller. That is the mass of a very small speck of dust. 10 to the negative 9, 1 nanogram. A pico is our next prefix. A picofarad, that is a small capacitor in a radio. We will learn what capacitors are. They have to do with conducting electricity. That's just that's a measurement, 10 to the negative 12. A femtometer. So a femtometer is 10 to the negative 15 order of magnitude, and a femtometer is the size of a single proton. The single proton. And then we have 10 to the negative 18 order of magnitude. That is an atto, or in this case, an attosecond. And that is the time it takes for light to cross an atom. So we went from the time it takes light to travel in 100 years to the distance it takes light to travel in 100 years to the time light crosses an atom. So that is order of magnitude as best, hopefully, this has cleared up. So now let's talk about unit conversion and dimensional analysis. When we are solving calculations in physics or chemistry or biology, or this is basic algebra. Unit conversion and dimensional analysis. In physics, it's often necessary to convert units from one type to another. For example, let's convert, and we'll do that down here. We will convert 80 meters to 1 kilometer. To perform this unit conversion, we're going to need what we call a conversion factor. To do this, we need a ratio expressing how many of one unit is equal to another unit, such as 12 inches in 1 foot. This is our English units. And 100 centimeters in a meter, or 60 seconds in 1 minute. Our conversion factor, and according to our order of magnitude, if we go back to the chart, the prefix kilo should tell us that this is a 10 to the third power of a meter. So we can very quickly, looking at this, know that and this is because of the simplicity of SI units, or the elegance of SI units, I should say, is that 1 kilometer has 1,000 meters. So we will set up our dimensional analysis. So we have 80 meters, and we want to know how many, what that is in kilometers. So we would multiply that by the fact that in 1 kilometer there is 1,000 meters. Essentially, we are dividing here. So if you wanted to, you could set it up like this. But as we get into more complex calculations, it is actually, and unit conversions, it's nice to have to show your work as it's done, and so that you can go back should you encounter an error, and you can very easily tell where you may have failed to convert a unit. So if you let's go ahead and solve this on our own. Okay, so let's practice some more calculations. Let's calculate some average speed. Suppose you are driving home or driving from school to your house you drive 10 kilometers from your school to your house in 20 minutes. Let's go ahead and calculate our average speed in kilometers per hour. So I'll give you a second to go ahead and do that. Okay, hopefully you noticed we're converting one of our units in part A. We're converting 20 minutes up here into hours. So if you didn't know, your conversion factor, there are how many minutes in 1 hour? There are 60. In 1 hour, there are 60 minutes. So maybe that can help you with your conversion and calculation of average speed. Now, let's go ahead and take whatever your calculation in kilometers per hour is, and let's go ahead and convert that into meters per second. Okay, so you've had some time now. Let's if you took your what you solved in part A and part B, you should remember now we have two units to convert here. So here's your conversion factors. In 1 kilometer, there is 1,000 meters, and in 1 second, or 1 minute, since we converted before we converted minutes to hours, now we're going the other way. So in 1 minute, you should know that there are 60 seconds. one thing to be careful of is that, when you go ahead and solve this, so if we were solving this, we would put 10 kilometers over 20 minutes. Whenever you are trying to cancel a unit, you need to make sure that whatever unit you're canceling is in the opposite, whether it's the denominator or the numerator opposite. So when we use this conversion factor here to get kilometers into meters, what we're going to want to do is we're going to want to be able to cancel that. We're going to want to put it actually like this and put 1,000 meters over 1 kilometer, and what that will do is it will cancel the units from the numerator. So that's a little hint. Go ahead and solve for this now if you have not already. So accuracy, precision, and significant figures. Oh, how fun. So accuracy, we're going to define accuracy here, is how close a measurement is to the correct value for the measurement. So if we look at our target here, and we see these 3 dots, or 4 dots, these 4 dots, they are all very close to the bullseye of this target. They have high accuracy, but they are low in their precision. High accuracy, but low precision. While precision is how close the agreement is between repeated measurements. So when we take a look at this target and we see our 4 dots very close in proximity to one another on the target, what we have here, but they're not close to our bullseye here. They have missed the bullseye, but they are all within the same area of one another. They have low accuracy and high precision. Low accuracy and high precision. So this is just a brief excerpt on that concept, the concept of accuracy and precision. When we measure in science, we want to be both accurate and precise. And so we like to use what we call significant figures, or sig figs for to abbreviate them. They are often abbreviated as sig figs, but that just means significant figures. So here are our rules. These are our rules. We will abide by them at all times for significant figures. 1, 2, 3, 4, and 5 cardinal rules to abide by for significant figures. All non-zero figures are significant. All non-zero. So we look at this example right here. 721 millimeters. 7, 2, and 1 are all non-zero figures. They're not zero. We have 3 sig figs here. When a 0 falls between non-zero digits, that 0 becomes significant. So here we have another measurement, 106 Kelvin. 106 Kelvin, that has 3 sig figs as well. And when a 0 falls after a decimal point and after a significant figure, that 0 is also significant. So we go down here to our third example for our third rule, 1.50 liters. So this 0 right here, this 0 is after this decimal point, and it falls next to a significant figure because this is a non-zero figure, making it significant. We still have 3 sig figs. Yes, I know. Astonishing. And rule number 4, when a 0 is used merely to indicate the position of the decimal point, that 0 is not significant. So our example here, 121 or 1,210 meters. 1,210 meters. Here we have a 0. All this 0 is indicating is that it's not shown here, is that there is a decimal point here. Thus, in 121, we have 3 sig figs. And then our next example, 0.053 meters. Now, I know a lot of you are jumping out of your seats saying it has 3 significant figures, but you would be wrong. So this 0, while it is, if we go back to rule 3, it is after the decimal point, but it is not after a significant figure. All this 0 is doing is indicating where this decimal point here is. So we only have in 0.053, there are only 2 sig figs. And then this last rule, it can confuse if you're not confused already. All counting numbers and exact numbers are treated as if they have an infinite number of significant figures, 10 pairs. So if I am counting objects, they are treated. So if I'm counting students, if I count students in a class and I come up with 33 students, those are all significant figures. If I count 36 students, significant figures. Exact numbers, counting numbers are treated as they have an infinite number of significant figures. But all these digits above were measurements. 721 millimeters, 106 Kelvin, 1.50 liters, 1,210 meters, and 0.053 meters are all measurements, whereas they are not counting numbers, and they're not exact numbers, they're measurements. But all counting numbers like 36 and 33 students are counts and exact numbers, so they are treated as if they have an infinite number of significant figures. All right, so let's check your understanding of significant figures. On the right side of your notebook, go ahead and write down right over here A, B, C, D, and E. Write down the examples and go ahead and tell me how many sig figs are in each. Go ahead and take the time to do that now. Okay, so hopefully you went ahead and took the time to do that. Now, let's talk about how many sig figs we have in each of these. So, in example A, how many sig figs? One sig fig. Why 1 sig fig? So, again, the zeros in this number are placekeepers that indicate the decimal point only. The only digit that is significant is this one right here, the 9. Part B, 15,450. 15,450.0. How many sig figs do we have here? Count them. 1, 2, 3, 4, 5, and 6. Yes. 6 significant figures. I'm sure a lot of you said that there were only 4. Here, the zeros indicate that a measurement was made to the 0.1 decimal point, the 10th. So the fact that we have a 0 beyond this decimal point makes it significant. C, part C. How many significant figures do we have here? 6 times 10 to the 3. How many? Let's count them again. We have 1. We just have 1 here. 10 to the 3rd. 10 to the 3rd is just our order of magnitude. It's just the order of magnitude, folks. It does not count as a significant figure. D. 87.990. How many significant figures? You should all be saying 5. 5 significant figures. The final 0 indicates that a measurement was made to the 0.001 decimal point. So it is significant. And it's to the right of a significant figure, making it significant if we go by our rules from before. E, 30.42. How many significant figures? 4. We have 4 sig figs. If we take a look at them, we have a 3, we have a 4, we have a 2, all non-zero digits. This 0 falls between 2 non-zero digits. It's not just indicating where this decimal point is. It is significant as well. So we have 4 significant figures in E. All right, sig fig calculations. The number of significant digits in the final answer can be no greater than the number of significant digits in the least precise measured value. Okay, so we have 2 rules for using significant figures in calculations here, and I want you to remember these as well, as we're going to abide by these during the course of our investigations. For multiplication and division, the result should have the same number of significant figures, as the quantity having the least significant figures entering into the calculation. Here, I'll go ahead and give you an example. So, if we are calculating the area of a circle, we would use the equation area equals pi r squared. Now, as we may be aware, pi is a very long number. To give you an idea here, let's give you some digits of pi. 3.1415, and it keeps going. As far as we know, pi goes and goes and goes. But if we're calculating this area and we use a radius of 1.2 meters, this digit only has 2 significant figures. So when we go ahead and calculate, we're going to get a long answer because we're using pi, but if we abide by our multiplication rules for significant figures, when we express our answer, even though if we put this into a calculator, we're going to get 4.5238934 meters squared. We only want 2 sig figs because we're abiding by our sig figs rules. So we can say that the area of this circle is 4.5 meters squared. Now, let's go to addition. Addition and subtraction. Addition and subtraction, the answer can contain no more decimal places than the least precise measure. So, let's say that we are buying 7.56 kilograms of potatoes in a grocery store as measured with a scale with precision to 0.01 kilogram. Then we go ahead and drop off 6.052 kilograms of potatoes at our lab as measured by a scale with the precision of 0.001 kilograms. Finally, you go home and you add 13.7 kilograms of potatoes as measured by a bathroom scale with the precision of 0.1 kilograms. So how many kilograms of potatoes do you now have, and how many significant figures? So if we look at our first measure in the grocery store, we have how many? 3 significant figures. Our lab scale, more precise, we have 4 significant figures. Our scale at home in the bathroom, 3 significant figures. Our answer can contain no more decimal places than the least precise measure. So when we go ahead and we subtract 6.052 and then add in 13.7, we should come up with 15.208 kilograms. But we want to express this with the proper amount of significant figures. So we are going to say, we're going to say that we have 15.2 kilograms of potatoes because we our least precise measured value had 3 significant figures, so our final calculation will have 3 significant figures. Thank you for watching, and hopefully this made sense.